Cool, thank you, Kazaya. Just gonna share my screen. Yeah, just the whole desktop. All right. That's not the beginning. All right, can everyone see in here?
Yep.
Awesome. All right, so thank you all for coming to my graph theory talk. I'm going to be talking about graph theory. Specifically, I'm going to talk a little about its origins, and that's with the bridges of Königsberg, I think I'm pronouncing that correctly. And then I'm going to talk also a little bit about what I would argue is by far its most famous implementation, which is the PageRank algorithm, which is the original algorithm that Google used to sort the internet. So let's dive in. So just right off the bat, a very high level, and like, please excuse me if this isn't very helpful information, because it kind of isn't, but what is graph theory? I think Drake is really saying it best here in that I think a lot of people hear graph and they think chart. It is not a chart. It is in fact this object down here, which is a bunch of dots connected by lines. It's also a branch of discrete math, which means that it's not continuous, and it's widely accepted to be part of combinatorics, which is kind of a fancy way of saying difficult counting. And it's specifically a study of pairwise relationships, and you may also hear it referred to as network analysis. All right, so you might be like, what the heck does that mean? We will get there. All right, first and foremost, 7 bridges of Königsberg. So Königsberg, Prussian, old-time Prussian city, current Russian city, actually in a very strange part of Russia that is not contiguous with the rest of Russia. That's a whole other thing. All right, so there was this ancient problem or old problem in Königsberg that was kind of like a mind teaser. It was a puzzle that like the locals were into, and it kind of stumped academics of the time. And the issue was they have these 7 beautiful bridges, and this whatever society of bridge aficionados were like, hey, we want to cross each bridge. We want to see every bridge in its full glory, and like we don't want to like see them twice. We just want to see each bridge one time. And so the problem arises that no one was able to do this. It was a famously difficult problem. No one could solve it. It also was tricky because it didn't really fit into any like prescribed existing branches of mathematics. They were like, oh, it's not geometry, like the shape of the island or the angle of the bridge. It doesn't really matter. And so the difficulty really was in the conception of how to even approach this problem. But thankfully, it got famous enough that attracted the attention of this man. If you don't know who this is, Euler is like the Mozart of mathematics. He's kind of a freak. He was a Swiss mathematician, et cetera, et cetera. He got educated by the Bernoullis, famous for their principle. He actually wrote the like most widely published version of that, so he kind of made it better for them. And yeah, he was just like prolific. Published 92 volumes, 56 years. He went blind at 59, and he was like, great, now I have fewer distractions. He had all these, after he went blind, he was even more productive because he had all these scribes who would come, and he would just like sit in his hospital bed and be like, yes, abstract numbers. Now, let me tell you about them. And he produced like a mathematical paper every week. So this problem attracted his attention. He showed up and sort of ruined it for everyone. He was pretty much like, hey, in fact, it's impossible to do this, and I will tell you why. And so his real innovation, though, was the abstraction of this problem and the framing of it. So he said, like, hey, again, like, the qualities of the bridge or the island themselves are irrelevant. There's no, like, special island shape that will let you do this. So what he did was he turned it into really the world's first graph. And so here are some definitions for you as I reference these things. And so he was like, all right, each landmass will become a vertex, and each bridge that connects them will become an edge. And so, all right, so like, so that was his way of breaking it down to its most base components. And that for him was how he was like, okay, like, here's how I approach this problem. It's really about moving between different points along these different edges. And so, and really when you break it down here and you try the problem itself, it becomes pretty obvious that it just like cannot be done. And so here, this is an attempted traversal. And so this was the graph shown above. And we'll just do a couple steps here. And so if we go from and so know that like as you progress across this path, if you cross a bridge, it is essentially eliminated from the running. So if you say, hey, I went over bridge AB1, now you can't go over that bridge again. So as we traverse each one of these edges, we'll delete it from the graph. And so, all right, so first we'll go from A to B, and then we'll go from B to D, and we'll delete those edges as we go. And so you can see A to B, B to D, we've created this dead end down here, which is kind of implying like, hey, like if you want to get here, you better end at B, you better come down here. And then the next traversal we'll do is from D to A and from A to C. And so then once we delete those, we find ourselves at C, and I think it's quite obvious that you realize that, hey, like I'm faced with two dead ends. If I go either way, I fail. And you may wonder why that is. It's actually a very, very simple explanation for this. And so imagine that like you're on an arbitrarily large graph, like it could be of any size, right? And you're crossing a bridge and approaching an island. In order for you to continue on your way, you need another bridge, and you need an exit bridge from that island. And you also need that entrance bridge as well as you're coming in. And so there's this kind of this pairwise relationship, right? Where it's like both to enter and to exit, you need a bridge. And so it turns out that is really all that was needed, was just this pairwise relationship. And so this is a very simple solution here. And so for graph G, it has to be connected. Obviously, if there was an island with no bridges, you could never get there. And then here's the meat of it, is that G must have exactly 2 or 0 vertices of odd degree. And so that means that you always have to have that, you always have to hold that pairwise relationship when you're crossing, when you're traversing this thing. And if at any point you reach a vertex with an odd number, you know that eventually you'll come around and suddenly there'll be one left. And so that becomes a dead end. And then the additional corollary is just that if you do have those two odd number vertices, one of them must be the beginning and the other one must be the end, because you are either starting there or getting trapped there. Any questions, comments, thoughts at this time? This makes sense to people?
So if you deleted one of the bridges from the last place, the one on the right, it would work?
Mm-hmm. I think, yes, it would, because...
if you deleted A to D.
Mm-hmm. Because then you're turning two, now you're stuck with only two odd, two vertices of odd degree. So yes, it would work. And right, you can even see here in this last one, right, if we deleted C to D, it would work too. Or yeah. Excellent inference. So right, pretty simple, really straightforward, but like really like the important part is to impress that like literally no one could solve this. It was like considered to be like an impossible problem. And then Euler came along and he had this really, the huge insight he had was this abstraction to say like, hey, like none of the qualia around, you know, these things matters. All that matters is this pairwise relationship between points and sort of the study of the network of the bridges. And like, because it didn't, in doing so, he kind of pioneered this whole branch of mathematics because it just had never really been thought about like that. And yeah, and so that's the very beginning. And now we get to PageRank. And so PageRank is crazy. So the problem with PageRank is, all right, so say you're building Google, right? And you're like, cool, like we can scan these websites for search results, but you know, if you search for sourdough, you're gonna get 33 million results back, right? And like, if you're trying to deliver a valuable product, a pile of 330 million unsorted things is deeply useless and is actually, you're like harming probably the person you're trying to help. And so PageRank was really like their way of ordering these things. And it honestly comes from sort of a similar abstraction where they went, you know, hey, like the words, like once we include these websites into this set of whatever sourdough results, the contents of the website is irrelevant to PageRank. They don't care about what's on it. They just want to know about the relationship, the links between them. And so, you know, along come these two folks. You may have heard of them, Sergey Brin, Larry Page. PageRank is named after Larry Page. You know, if you want to get your algorithm named after you, make sure it puns with what you're actually working with. Sorry, Sergey. But yeah, so and their big quote here is that PageRank works by counting the number and quality of links to a page to determine a rough estimate of how important the website is. The underlying assumption is that the more important the website, the more likely it is to have more links from other websites. And so like, this is actually really clever because it's like, this is like 9 out of 10 doctors recommend this page, right? Like they're not really making a statement about the contents of the page itself. They're just saying like, hey, other people really like this website, so we think you might too. And you might say like, wow, how do you do that with, you know, the web graph of all websites? And like, how does one reach this state? Well, here we go, implementing PageRank. And so we're going to start with this really simple graph here of just a network of 4 pages. And so it's important to note that I think in the first implementation of PageRank, they distributed a value of 1 to every single page, but now we do probabilistic model, and so we split the value of 1 across all of them. And so this is an iterative and recursive algorithm. It's also worth noting that the web graph is a directed graph as opposed to the bridges where the links are one directional. So like this link only goes this way as opposed to both ways. Like you go back and forth on a bridge, a web link, not the same. And really like the intuitive nature behind this algorithm, I believe is like quite straightforward. So you start off initializing everything with the exact same value. And then this interstitial stage happens where, okay, so look at D. You start with like you pick a vertex, you look at how many outbound edges it has. And then you simply divide the value it has at that vertex by the number of outbound edges and essentially send that value along that edge. And so that's what's happening here. You can see that B has been split into 2 parts, D has been split into 3 parts and is being sent to all of its linked pages, as is B, and then C is just split into 1, so it sends everything to A. And then, so this would be the first step of PageRank calculation for these pages. And then this is actually calculated recursively and iteratively, so they'll feed this result back into the same algorithm until it converges within a certain degree of accuracy. And that's pretty much how it works. There's actually a couple things missing here if anyone wants to chime in and see a problem that might arise from this. Any takers?
So I don't think this is the actual problem, but like this is making me think about like search engine optimization, like adding in keywords to a site to like higher up the rank of the page, to show on like the first page. So like I feel like that could possibly, like SEO could possibly like conflict with like with the links.
And like and your point is great too. Like you're totally right, and that is a huge problem with this, in my opinion, is that it's like a known measure, and so people cheat to it. And it's also worth noting that PageRank is not the algorithm they use currently. There's like some PageRank Plus that's proprietary that only whatever Google quants know about. So there is more to it than this. And yeah, you're completely right. I think that's William. I see it.
Yeah.
Cool.
I remember there being link farms where you could literally pay them and they would add your link on like, 1,000 websites and you'd get a little bit more
exactly
a higher rank.
Yeah. And
the solution to that was to simply take all the sites and not make them equal in terms of value.
Right, and they do that as well. Like there are some, like if you're coming from WebMD, like they assign some weight to that. And what is super cool about this algorithm, and I think it's visible up here, is that with this B to C relationship, like this initially I think looks really weird because you're like, wow, C is only linked to one other page, but because it's linked to B, which is so important, like the recommendation of an important page carries more weight to it. And since B is only recommending C, every time it trades a value with anyone, it's just sending it to C. And so it kind of like internalizes the idea that like of experts or sites that are more reliable or more important than other ones. But there are two things algorithmically that are missing here. One is what the hell happened to A? If you might notice, like this had 0.25 and it's suddenly gone. So this is an issue. This is called a sink, where this has no outbound links at all. And so in the naive formula down here, where you're dividing by the number of outbound links, this introduces a division by 0, which is a problem. And do you think this is rather rare on from a page perspective? Like, you're not going to find a lot of pages with no outbound links. But their solution for this is they literally just like send this to a random other page. They're like, hey, have nowhere to go? Pick anything. And you know, the graph is large enough that it works. And then there is also a dampening factor, which is when to stop. And so, right, if you kept iterating that infinitely, everything would converge into like a couple different pages that had either sinks or had tons of links. And so they introduced this randomized stopping factor to essentially allow like a page that has no links being sent to it, like that can still have a value because someone might stop there. And they're also each iteration is kind of supposed to mimic someone browsing the web. And they're saying, like, you know, people do not browse the web infinitely. Like, you browse it for a finite amount of time and then you stop. And yeah, the drawbacks are definitely as the link farm thing, cheating to the measures, big deal. It also favors existing pages. So if you like create the best ever sourdough page and put it up on the internet and no one links to it, then Google sort of doesn't know it exists or doesn't know it's important. So it's not like perfect. But I mean, for what it is, it's amazing. It also has a log n scale, I believe, as size scales up. So it's very efficient. And then here's a bonus at the end. This is one of my favorite graph theory problems. All right, here's the context. Mr. and Mrs. Smith are having a party. They invite 4 other couples. There are 10 people now in total at this party, including Mr. and Mrs. Smith. Mr. Smith, at a certain point of the night, goes to the kitchen. Now there are 9 people remaining in the living room. This is the like staging for this problem. So Mr. Smith stays in the kitchen. These 9 people stay in the living room. All right. And now each of these 9 people know a different number of people at the party. And so the most you can know is 9. The least you can know is 1. Each person knows their partner, and knowing yourself does not count. And now, knowing all of this, the question is, how many people does Mr. Smith know? And that's it. That's all you need to figure that out. If you start drawing it and connecting stuff, I guarantee you can get it. I will not tell you the solution now, so you can all agonize over it if you want to. Yeah, that's pretty much it. Thanks for coming to my graph theory talk. Questions, anyone? Thoughts?
Are you going to give the answer next time?
Yes, I will.
Oh, good.
And if you message me, I will definitely talk you through it. It's like I promise you, if you start to draw this problem and like draw it like a graph, you will get it and you'll feel great about it.
So this question has to do with who Mr. Smith knows personally, or like through his wife. So like, he definitely knows his wife. So then his wife knows 3 other people. So that he knows 4 people now?
No, knowing through another person does not count.
Got it.
So like if we showed up at the party together and you knew someone, I don't necessarily know that person. Like, it's not, there's no transitive property between knowing.
And just to be clear, nobody invited a +1, right? The Mr. and Mrs. Smith invited each person jointly?
Not necessarily.
They were random invitations.
Okay.
It was a lottery.
And the importance of the kitchen?
The importance of the kitchen is just that so 9 people are left remaining in the living room, so they can all have distinct numbers of knowing. Draw it, for sure. This was the first homework problem in my graph theory course.
The hint is nobody knows 1.
That's true.
Nobody knows only one.
That is not true. Someone
That is,
does know one.
you're right. You're right.
Okay, so while people mull over it for a bit, any other questions?
Do you guys feel like you got like absorbed some knowledge here? Was I just like talking to the wind? I don't know.
Absolutely fascinating.
Good.
Really, really good.
Thank you.
William, you look like you were going to say something.
I was just agreeing with how fascinating it was. It was awesome.
Nice.
Yeah, it's like my favorite subject, personally. And I want to do a couple different talks on this too, and eventually we'll get to doing analytical modeling in graph theory models, which is really hot right now in the analytics world. It's pretty cool. There are actually there's a database called Neo4j that is a graphic database or a graph database, and you can write queries in it as pictograms, which is like the best thing that's ever happened to me in my life. So stay tuned.
A visual programming language? Is that what you're talking about?
It's a visual database language. In a visual query language. So kind of, yeah. Cool.
Any other questions? I think people are just excited to try to solve this problem.
I hope so.
I started graphing it.
Yeah, do it. Seriously, anyone message me and I will like jump on a video call and we can talk about it because I love this stuff.
Can you try explaining one more time why it's important that he goes to the kitchen? I don't see how that makes a difference in who knows who.
It does. I'll tell you that is a key part of this problem, but I will not spoil it. Again, it matters because there are only 9 people left, and then there are 9. Everyone left in that room knows a different number of people from 1 to 9.
And is it how many people does Mr. Smith know in the room, or just like in the party in general?
In the party.
Including
But
his missus?
it would be including, right, everyone knows their partner. So Mr. Smith definitely knows Mrs. Smith. You know, if you came with someone, you know them, but you don't necessarily know the people that they know. I would think that, to me, the key of this problem are to think about the extremes. Like really think about the person that only knows one other person. And once you start to like put that puzzle piece together, everything else kind of like follows from it. But I've said too much, I think.
Yeah. I think so.
Yeah, Hirsch is like, I got it. All right, guys, I'm gonna stop sharing my screen.
Okay, we will share the result, I guess, next week.
Yes.
The talk. And
Yeah, thanks everyone.
yeah, feel free to reach out to Jackson if you feel like you solved it or have some questions there.
I'm expecting at least one person.
Yeah. Great job, Jackson. Thanks so much. Alex already clapping with his emoji.
Yeah, thank you.
Quickly. And I guess that's it for today. Thanks, everyone.
All right.
Thank you. That was great. See you.
Bye, guys. Thanks so much.
Bye.